Hello students. Today in this video I am going to discuss two important topics of the chapter redox reaction of class 11. The name of the topics are oxidation number method and ion electron method. Okay, let us begin. So as you can see here, redox is the short form of reduction and oxidation. So redox reactions are those reactions in which oxidation and reduction takes place simultaneously. Most of the students, those who don't know what are these oxidation reactions and reduction reactions, let me explain it to you. Oxidation reactions are the reactions in which either oxygen or any other electronegative element is added, or hydrogen or any other electropositive elements are removed. Similarly, reduction reactions are the reactions in which hydrogen or any other electropositive element is being added. Also, oxygen or any other electronegative element is removed. So we can say that oxidation reaction and reduction reactions are inverse to each other. The reaction in which both these type of reaction, that is the oxidation reaction and the reduction reaction, takes place simultaneously are known as the reduction reaction. Now, if you look down, you can see there are two ways to balance a redox reaction, because any type of reaction that we get in the book or anywhere else, sometimes it is not balanced. So we try to balance it before we go further. So there are mainly two ways: oxidation number method and ion electron method. Before proceeding any further, you need to know some of the mandatory rules for assigning the oxidation number to any type of atom. Oxidation number of hydrogen is always +1, but in case of hydrides, it is -1. In case of oxygen, the oxidation number is always -2, but in case of peroxide it is -1, and in case of superoxide it is -1/2. As you go through the point, you can see in oxygen difluoride it is +2, and in case of dioxygen difluoride it is +1. The oxidation number of fluorine is always -1 in all its compounds. As you go through the successors, that is the chlorine, bromine or iodine, the probability of changing or the change in the oxidation number is quite possible, means the oxidation number varies. But in case of fluorine, in most of its compounds it is -1. For the neutral molecules, the oxidation number is always 0. Also in case of free or elementary states, the oxidation number will be 0. In case of ions composed of only one atom, like Na plus and Cl minus, in case of Na plus it is +1, in case of Cl minus it is -1. That is the charge of the ion. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. So let us assume in a compound like HNO3 that you will get further. So HNO3, from the above points I know it is, for hydrogen it is +1. For nitrogen, I don't know till now. In case of oxygen, I know it is -2. So in case of HNO3, the oxygen and hydrogen have their respective oxidation number, that is default oxidation number +1 and -2, right? So by calculating, I can easily find out that +1 and -2, as we have 3 oxygen in HNO3, it is -6, and +1, that is -5. As it is said here that it must be 0. So to make -5 0, what is to be added? That is +5. So from that method, I can easily find out the oxidation number of nitrogen is +5. That is totally from the concept of this statement, that is the algebraic sum of the oxidation number of all the atoms in a compound must be 0. Similarly, in case of ions, the sum of the oxidation number is equal to the charge of the ion. Already we have seen in the previous points. Also in a polyatomic ion, the algebraic sum of all the oxidation numbers of the atoms of the ion must be equal to the charge of the ions. Means in case of ions, the main thing that we have to keep in focus is the charge of the respective ions, whether it is a single element or it is a complex compound. Understood? In the first method, that is the oxidation number method, you will get a type of reaction that you are seeing here, that is P plus HNO3 arrow HPO3 plus NO plus H2O. The first thing that you need to do is to write the oxidation number of all the atoms present in the particular reaction. Here for phosphorus, as it is a single element, so the oxidation number will be 0. You should abide by the rules that you have just seen in the previous slides. Okay, so for P, the oxidation number is equal to 0. The next thing, that is in HNO3, we know from the rules that the oxidation number for hydrogen is +1, for oxygen it is -2. I have already done on the right hand side of the clip for HNO3 and HPO3. This is a rough thing, that how to find out the oxidation number when you have hydrogen and oxygen. See, for hydrogen it is +1, for oxygen it is -2. As you see downward, for hydrogen I have written +1, for oxygen it is -2 into 3. So the total thing that we have is -5. In order to make it neutral, according to the rule, we need +5. So the oxidation number of nitrogen is equal to +5. Similarly, in case of HPO3 also, if we go through the same process, we can see that the oxidation number for phosphorus is also +5. For NO, here, in order to make the compound neutral, it is NO. The oxidation number for oxygen is -2, so we need only +2. So the oxidation number for nitrogen is +2. Also in case of water, we know for hydrogen as well as for oxygen. If I place it for oxygen, that is -2, we will be needing +1. That is, to make it neutral, we have to make it 0. So there is a -2. So if we write +1 into 2 is equal to +2, +2 minus 2 is equal to 0. So all the elements here are neutral and with their respective oxidation numbers. If you go through the second step, you can see the variation in the oxidation number. In the reactant side, the oxidation number for phosphorus is 0. But in the product side, the oxidation number for phosphorus is +5. Also, in case of nitrogen, in the reactant side it is +5, in the product side it is +2. So I can see here that in one side there is a deficit of electron, on the other side there is a surplus of electrons. So I can basically see that phosphorus is having the oxidation reaction and nitrogen is having the reduction reaction. In the third step, what we will do is we will balance the oxidation numbers. See, in the first step number 2, you can see that in the case of phosphorus, there is an oxidation number of 5. In case of nitrogen, there is an oxidation number of 3. So there is a difference of 2 or not? The 2 electrons are not butterfly that they can go away, right? So in order to make or to balance the oxidation numbers, we will multiply 3 on the upper hand side. That in case of phosphorus, we will multiply it by 3. In case of nitrogen, we will multiply it by 5. That is, now we have 3 molecules of phosphorus and 5 molecules of nitrogen. Means 3 molecules of phosphorus will be donating 15 electrons and 5 molecules of nitrogen will be accepting 15 electrons. Understood? So just in the fourth number step, I am just writing here that I had just described that 3 molecules of phosphorus that have given that 15 electrons is being accepted by 5 molecules of mainly nitrogen, right? And after that, you can see here in both the sides, that is in the reactant side and the product side, I have multiplied it by 3. In the upper hand, on the side, step number 3 only, we have done that, right? In both the side, we have multiplied it by 3 in case of phosphorus, and downward, we have multiplied it by 5. So now it is 3P plus 5 HNO3 arrow 3 HPO3 plus 5 NO plus H2O, and the reaction is totally being balanced. Understood? Now we have come to the second method, that is the ion electron method. As you have seen in the oxidation number method, the first step will be same in case of ion electron method also. Here also, in a given reaction, you just need to write the oxidation numbers of their respective atoms by following the rules that you have just read in the previous slide. Understood? So just see the reaction. Cr2O7 2 minus plus Fe2 plus H plus arrow Cr3 plus Fe3 plus H2O. Here in the complex Cr2O7 2 minus, here if I go by the rules, for Cr, that is for chromium, the oxidation number will be plus 6. For oxygen, we already know it is minus 2. In case of iron, it will be the charge, that is the plus 2. In case of hydrogen also it is plus 1. In case of chromium also it is plus 3. In case of iron again it is plus 3. In case of water, in upper hand of the hydrogen I will be writing plus 1, and in case of oxygen I will be writing minus 2. So see, when you read or when you memorize the rules or just understand it, right, you can easily do the oxidation numbers. One thing I want to mention that in your boards, in case of SEBA, it is the board. In case of CBSE, just class 11, there will be one question to find out the oxidation number also. So better read the rules such that you can easily get it 1 mark. Also for this ion electron method, the question that will be given to you, a reaction will be given to find out through the oxidation number method or the ion electron method. The minimum marks will be 2. See, from this reaction only you are getting, if you go through this video nicely, you are getting 3 marks. And from redox reaction, the marks come either 3 marks or 4 marks. So you will be getting the full marks, isn't it? So just go through it nicely. Okay, where were we? Okay, so just after writing the oxidation number, you can see in the second step that we have separated the reactions into 2 half cell. And we know what are the 2 half cell, that is the oxidation half cell and the reduction half cell. What is this oxidation? Where oxidation reaction occurs, that is, it donates Fe2 plus tends to Fe3 plus, means it is donating the electron. So here iron justifies in the oxidation half cell, and in case of chromium, you can see chromium we have plus 6, in the product side we have plus 3. So here we are accepting the electrons, so I can easily put it in the reduction half cell. So now you understood how you can put an element by studying its oxidation number. By just seeing its oxidation number, you can easily say which element will go in the oxidation half cell and which element will go in the reduction half cell. In the third step, now we'll be balancing the atoms. See, in the oxidation half cell, here Fe2 plus tends to Fe3 plus, we have only one atom. For iron, in the product side also we have one atom, in the reactant side also we have one atom. But in case of reduction half cell, there is Cr2O7 2 minus tends to Cr3 plus. So in case of reactant side, we have 2 chromiums, but in case of product side, we have only 1 chromium. So in the next line, I have balanced it by writing 2 on the product hand side. See now, Cr2O7 2 minus tends to twice Cr3 plus. Understood? Okay, till now we have balanced the chromium, but in the complex, that is of the reactant complex, is Cr2O7, we have 7 oxygens, right? So in order to balance the oxygen, we will be writing 7 water on the other side, that is in the product side I am writing 7 water. See, for 7 oxygen you have to always write 7 water, 7 H2O. Okay, so already I have written 7 H2O on the other side. Also, when you write 7 H2O, you will be getting 14 hydrogen extra or not, right? See, from the previous line, Cr is balanced, Cr2 twice Cr balance. For that particular 7 oxygens, I am writing 7 H2O, 7 water. Okay, now oxygen is also balanced. We have 7 oxygen, that's it. But in case of water, we'll be having 14 hydrogen or not. So on the other hand side, that is on the reactant side, I will be writing 14 H plus to balance the full reaction. So the net reaction right now in the reduction half cell is Cr2O7 2- plus 14H plus tends to, that is the arrow, twice Cr3 plus 7H2O. Now after the atoms were balanced, in the fourth step, we'll try to balance the charges. Again, we'll go to the oxidation half cell. Here Fe2 plus on the reactant side and Fe3 plus is on the product side. So means there is a what? There is a deficit of one electron, or sorry, one charge. So Fe2 one electron actually. So Fe2 plus tends to Fe3 plus. So I will be writing just plus one electron on the product side. Now in the oxidation half cell, the charge is being balanced. Now go to the reduction half cell. Here, in case of the complex, that is Cr2O7 2- plus 14H plus, here in the left hand side of the reaction, how many charge we have? See, for 14 hydrogen we have 14 plus charges, and in case of the complex we have 2- charges. So the net charge will be how much? Plus 12, isn't it? Plus 12. Go to the other side of the reaction. There, in case of chromium, that is, we have two chromium, that is twice 3 plus, so it is plus 6, isn't it? Plus 6, 3 plus charge, we have two chromium, so this plus 6 is the charge. In case of 7H2, there is no charge, right? So on one side we have plus 12, and on the other side we have plus 6. So on the left hand side there is a deficit of charge, isn't it? So in order to make the charge equal, I am going to add 6 electrons on the left hand side of the reaction. You can easily see on the second line of the reduction half cell, I have written, that is, on the left hand side I have written plus 6 electrons. So now we have plus 6 charge on the left hand side and plus 6 charge on the right hand side as well. Also, the charges were balanced. So in step 3 and step 4, we have balanced the atoms. Also, we have balanced the charges. Okay. In the step 5, we will be balancing the electrons on both the sides. That is, on both the half cells. Understood? Now, before seeing the oxidation half cell, just go to the reduction half cell. In case of oxidation half cell, we have Fe2 plus arrow, Fe3 plus plus 1 electron. Okay. As I have told you to go to the reduction half cell, because see the reduction half cell, we have Cr2O7 2- plus 14H plus 6 electron. Means in case of oxidation half cell we have only 1 electron. In case of reduction half cell we have 6 electron. In order to balance the electrons, we will be multiplying the oxidation half cell by 6. After multiplying, we have got the second line in the oxidation half cell, that is 6 Fe2 plus arrow 6 Fe3 plus 6 electron. Understood? Now in both the oxidation half cell, also in the reduction half cell, we have 6 electron each, and the electrons were balanced. Understood? Finally, in the final step, that is the step 6, we will be combining both the oxidation half cell and reduction half cell. Here the reactant parts will be on one side, on the left hand side obviously, and the product side parts, that is the right hand side parts, will be on the product part. 6 Fe2 plus from the oxidation half cell, then plus Cr2O7 2- plus 14H plus 6 electron from the reduction half cell. So the reactants were written on one side. Now go to the product side. From oxidation half cell, I have written 6 Fe3 plus 6 electron, written plus twice Cr3 plus 7H2O from the reduction half cell. So all the products were written on right hand side, all the reactants were written on the left hand side. Now I have just not shown it for my convenience, but you can just cut the 6 electron from both the side. That is 6 electron from the reactant side and 6 electron from the product side, as they are both equal. After cutting down the final reaction, that is 6 Fe2 plus Cr2O7 2- plus 14H plus arrow 6 Fe3 plus twice Cr3 plus 7H2O is your final balanced equation. See, in these 6 steps, you have balanced the oxidation numbers, you have separated the half cells, you have balanced the atoms, you have balanced the charges, you have balanced the electrons on both sides, and finally you have combined both the cells into one particular reaction. And that's how you have to do the ion electron method. Thank you so much and have a nice day ahead.